Hello. Now, in mathematical physics, we come across various helpful tools which help us perform the calculations in physics, which would have been otherwise very tedious. One such important tool that we come across is the Laplace transformation, or we just do the Laplace transform. Actually, I should extend the title of the story that we have to discuss today. So this is Laplace transformation, and we will be doing many such transformations, uh, and the Laplace transformation are a helpful tool, as you would see, in determining various integrals, such as the solutions to the differential equations which have the boundary values without finding the general solution and the values of the arbitrary constants. So let's get to the definition of the Laplace transform first. So firstly, we have the Laplace transform. You can call it Laplace as well. So the Laplace transform can be defined. I'm straight away giving the mathematical definition of it without wasting further time. So if we have a function, suppose f of t, so for a function f dependent on t, for which is defined for all the positive values of t, we have f s as its Laplace transform when it is integrated from 0 to infinity e raised to the power, that is the exponential of the negative st, s times of t, multiplied to f of t, which is the given function, all integrated over dt, provided that the integral exists, and this is what we term as the Laplace transform of ft. So this is the Laplace transform of ft, which is the capital F of s. We denote it, so it is denoted as L, which is the notation for the Laplace transform of f of t, and that is obviously equal to f of s, which is again equal to this term that we have just given or just provided. Now, some of the important formula that you can get from this transform is what I'll be writing down. So these are some of the important formula that we can use to our benefit. Supposedly the first one being Laplace transform of 1 is going to give us 1 over s. What we are going to do is we can put that 1 in place of that f of t, which is the last line that I've written, and we carry out the transformation as provided in the integration, that is integration from 0 to infinity e raised to the power minus st f of t. Instead of f of t, we have of the value 1 over here and integrated over dt, so that would give us 1 over s. Obviously s is of a value greater than 0. And then we have for the second case the Laplace transform of t raised to the power n, which is equal to n factorial over s raised to the power n plus 1. Similarly, and the values of n of course being 0, 1, 2 and so on. Now for L, that is the Laplace transform of e raised to the power at, that is the exponential of at, we have that value to be equal to 1 over s minus a, for s being greater than a. The fourth one, that is the Laplace transform of cosine, that's not hat, but that's cosine hyperbolic function of at, that is equal to s over s squared minus a squared. Obviously we have s squared to be greater than a squared. Where is that s coming from? Well, the s is that transformed term, because we have that e raised to the power st in that integrand, as you can see. And then we have the sine hyperbolic, the Laplace transform of the sine hyperbolic of at, that gives us a over s squared minus a squared, and the same condition that s squared is greater than a squared. The Laplace transform of s, that sine of at instead of the hyperbolic function, the general sine at, that is a over s squared plus a squared for s greater than 0. And we have the Laplace transform of cosine at, that is equal to s over s squared plus a squared. So now what I would do is I will try one of these formulas, the left hand side, that is, I'll try and solve it, and let's see if we are getting the numbers or the formula according to the formula what we have obtained in the on the right hand side. So I'll check for, suppose, let's see, what should I take? I would rather consider the fourth one, that is the cosine hyperbolic. I'll do one of them. You can try the rest of them for your proper understanding. Now, as far as that fourth one is concerned, we will try and look at the proof of it. I'll try just one, because these are just the formulas that have been provided. We will see that whether we are getting it or not. We'll obviously get it, but just to make sure that we are on the right track. So the Laplace transform of cosine hyperbolic at. Now the cosine hyperbolic at can be extended as the exponential of at plus the exponential of minus at over 2. Now the hyperbolic terms, obviously, as you know, are the real terms. They are not imaginary, so we'll have these things instead of the imaginary term that would have been e raised to the power iat in case of the general cosine and sine functions. The hyperbolic functions are devoid of those imaginary numbers or complex numbers. Now this Laplace transform is just going to be equal to the, well, we can take them separately. So we have a Laplace transform of e raised to the power at, and the 1 over 2 can go out. We can take that entirely as the common term. We'll leave it we'll save it for last, and then plus the Laplace transform of e raised to the power minus at, all of that multiplied with half. Remember, we had the 2 in the denominator. Now the Laplace, if we use this formula over here, that is the Laplace transform of e raised to the power at, then that is going to give me 1 over s minus a for the first one, while for the second one, because we already have minus a over there, so this will be 1 over s minus of minus a, which leaves me with s plus a, all of that multiplied with half. Now if I take the LCM, then we have s squared minus a squared, and at the top we have s plus a plus s minus a. The a's will cancel out. We'll have 2s, which cancels out with the 2 outside in the denominator, so we'll have only s, which is exactly the formula that we have obtained on the right hand side of that equation provided. So it's pretty easy to determine these values. In case you would have thought that, well, we didn't use any integration over here, well, we had the formula for that. Let's try a bit with a proof with integration involved. So I'll try it over here. The space is vacant, so I'll probably use it to my benefit. So let's see, we have the Laplace transform of e raised to the power at. So let's see that. That is the third equation, that is. So if we have f of t as e raised to the power at, which is the third one over here, then what we get is we get the Laplace transform as f of s, which is equal to the integration from 0 to infinity e raised to the power minus st. Now instead of f of t we have the exponential of at dt. So that's a minus s whole multiplied with t. So integrating that, what we would get is that a minus s term would go down. So we have the integration as e raised to the power a minus s times of t over a minus s, and then we have to take the limits of the integration from 0 over to infinity. Now if we put that value over there as 0, I'll probably try and continue over here for the lack of space at that point, so please bear with me. So if let's just take, because if we put infinity instead of t over there, then things will go pretty uh, indecent there. So what we do is we put the a minus s outside for now, because they don't have any role to play any further. And what we do is we take it as s minus a in that power term. So we have e minus of s minus a times of infinity minus, and anything multiplied to 0, because will be taking the lower limit as 0 for t, so we have e raised to the power 0. So now this minus infinity in the power is going to reduce it to 0. So this first term is going to go to 0. And what we are left with is 1 over a minus s multiplied to, well, this is 1. This is 1. So, and it is minus 1. So this will be minus of 1 over a minus s, and that gives us 1 over s minus a. So that is exactly the value that we have obtained over here. So similarly you can prove a lot many formulas that are there, that are present over there, and you can check for yourself. I would suggest you try the second formula now, and see for yourself if you are getting that n factorial over s raised to the power n plus 1. And you can easily get sine, cosine, and sine hyperbolics as well. Now with the assurance that we just obtained the formulas of Laplace transform, with the assurance at hand, we might probably look into some of the properties of the Laplace transform to start with. So the properties can be, some of the properties as of now can be laid down as follows. So the first property being the case of the Laplace transform of the sum of two functions, which is a times of f1, a linear combination over here of the two functions a times of f1 of t plus b times of f2 of t, and that will be equal to, well, the constants can come outside, those coefficients which were multiplied, they can come outside. So we have the Laplace transform of the first function, that is f1 of t plus b times of the Laplace transform of f2t. Let me write that clearly. Well, this obviously seems pretty straightforward. There should be no problems with that. Now we switch over to the next case, where we have the first shifting theorem. Now, as per this theorem, if we have the Laplace transform of f of t to give us fs, then we'll have the Laplace transform of e, the exponential of at times of f of t, to be equal to f of s minus a. We can prove this. Let's consider proving this one. So that's how I prove it, but where we take the Laplace transform of e raised to the power at f of t, and with the formula at hand, that is Laplace transform of anything is within the integrand we have e raised to the power minus st into that thing times of dt, and that is equal to, well, if we look at it, that we have e raised to the power at e raised to the power minus st, so that's exponential of negative of s minus a times of t. This is what we have over here, negative of s minus a times of t. In case it's not clear, let me write it clearly for you. Then we take s minus a as r, and with that expression of the integrand over there, that is from 0 to infinity, exponential of minus rt f of t dt takes us to the Laplace transform of f of r, and that is equal to means the Laplace transform of f of t for sure, but the variable that is multiplied to it is e raised to the power minus rt instead of st, so we have the function as f of r instead of f of s, and remember we have taken r as s minus a, so this is simply capital F, the function of s minus a, which is what we had to prove over here, the shifting theorem, that is. So we can use all these properties to our benefit, and let's see a few numerical problems that we can try with what we have learned. Now the first case that we can consider, now the first thing that we can look at is to find the Laplace transform of cosine squared t. Now as you know that for the solution we have over here, cosine squared t can be written as 1 plus 2 times 1 plus cosine 2t over 2, and the Laplace transform of that is 1 plus cos 2t over 2. Now that 2 can go outside, taking that 2 outside, what we get is we have half of Laplace transform of 1 plus cosine 2t, and that means half of, well, Laplace transform of 1 is going to be 1 over s, we know that, and cosine at is simply s over s squared plus a squared. Instead of a we have 2 over here, so s over s squared plus 2 squared, which is 4, and that eventually gives us the value half times of, we can multiply all of that and obtain the value. That's well, let me do that. S squared plus 4, and this is s squared plus 4 plus s squared, so this is 2 times of s squared plus 4, and that's going to be equal to, and half of that, so this is s squared plus 2 over s squared plus 4 times of s. So this is the value that we obtained for that given equation or that transformation. Now let's see the Laplace transform of t raised to the power minus half. Now for that we take the the Laplace transform of t raised to the power minus half is simply going to be, well, we can use the equation t raised to the power n, and t raised to the power n, the Laplace transform of that is, if you remember, is minus half. Half over here is n, so n factorial over s raised to the power n plus 1. Well, the minus half factorial that we have over here, that can be written in terms of the gamma function, that is equal to gamma n plus 1 is nothing but n factorial. So this is n, instead of n we have minus half over here, and so minus half factorial is nothing but gamma minus half plus 1, and this is s raised to the power minus half, so this is root over of s. That's okay. Now we have a gamma half over here and a root over of s. Now gamma half, as we know, is root pi, and this is a root s, so this is root over of pi over s. So that's the solution for this equation, or this transformation, that is the Laplace transform of t raised to the power minus half. We can do many more such questions, many more such uh, um, things can be easily obtained by using this Laplace transform. Now I'll leave you with two more questions for you. This is for you, the viewers who are watching this. So let's try, or you try. I'll leave it to you. I'll give it to you in the next video. So the Laplace transform of t sine at, and secondly the Laplace transform of t square cosine at. We'll do many more such questions. I've provided these two questions for your uh, uh, self-analysis. You can say a short assignment, which will be answered in the next video by me for sure, but you can try this. Till then, thank you for watching.